New data has revealed strange, undulating structures in regions of space that mark one of the boundaries between the inner solar system and what exists outside this bubble, known as interstellar space. As we will learn in this video, the information will help scientists better understand a region of space called the heliosphere, which radiates from the sun and protects the planets in our solar system from cosmic radiation. Make sure you stick with me till the end. Without any further delay, let's get into it. An unexplained ripple has been detected at the edge of the solar system. The heliosphere is the gateway to interstellar space, and it's a very weird place that we're just beginning to understand. A new study has reported that scientists have discovered weird ripples and unexplained structures at the boundary between our solar system and the vast expanse of interstellar space beyond it. According to the study, the obtained results show that the border of the heliosphere, a protective bubble created by the sun that envelops the solar system, shifts in ways that are intriguing and potentially controversial. The heliosphere extends some 11 billion miles out into space, more than twice as far as Pluto's orbit, and is sculpted by a stream of charged particles emitted by the sun called the solar wind. The edge of this structure is marked by a region called the heliopause, where the solar wind gives way to the forces of the interstellar medium. NASA's Voyager 1 and 2 probes, which were launched in 1977, both crossed this boundary over the past decade, making them the first human-made objects to venture into interstellar space. The Voyagers continue to send dispatches from beyond the heliosphere, but they can only report on the conditions at their specific locations. Scientists have learned to map some of the broader contours of the heliopause by looking for emissions made by energetic neutral atoms, ENAs, which are created by the interactions between the solar and the interstellar winds. But much of this transitional domain is still shrouded in mystery. Now, scientists led by Eric Zernstein, a research scholar in space physics at Princeton University, has identified curious new details about this zone that were illuminated by a months-long spike in the dynamic pressure of the solar wind that occurred in 2014. A NASA satellite called the Interstellar Boundary Explorer, IBEX, captured a dramatic brightening of ENAs in the aftermath of this pressure front, which revealed the motions of the heliopause and significant asymmetries in the structure of the heliosphere that conflict with models, according to a study published on Monday in Nature Astronomy, hence the potential for controversy. Zernstein said in an email that in early 2017, they noticed a brightening of energetic neutral atom, ENA emissions in Interstellar Boundary Explorer data coming from a small part of the sky, centered about 20 degrees below the nose of the heliosphere. He added that this brightening first showed up at the highest ENA energies they could observe. Then, over time, the emission area grew larger and larger across the sky and started to appear at lower ENA energies, he continued. He also highlighted that they knew this had to be in response to a big change in solar wind pressure, which is a key factor in determining ENA emissions from the edges of the heliosphere. The fact that the initial spot of brightening was not centered on the nose and expanded asymmetrically across the sky motivated studies of this behavior to learn why. As the researchers examined the Interstellar Boundary Explorer observations, they realized the surface of the heliosphere is distorted by huge ripples that appear at an unexpectedly oblique or slanted angle. These spatial variations within these structures can reach 10 astronomical units, AU, where 1 AU is the distance between Earth and the Sun. Zernstein also said that they were quite surprised about how oblique the surfaces are, where the closest points are tilted 30 degrees below the nose, in contrast to most known models of the heliosphere. He added that the ripple structures were surprising as well, because after they did their best to account for potential uncertainties in the analysis, they found these ripples to be statistically significant. But in hindsight, when they considered how dynamic the solar wind actually is, this probably shouldn't have been too surprising, but he stated that it sure was interesting to see it. According to Zernstein, the exact mechanisms that are producing some of these intriguing observations are unknown. He noted that there seems to be a missing driving force for this asymmetry that is connected to the solar wind and its interaction with the interstellar medium. Other star systems with astrospheres may be similar in their asymmetry, but it all depends on the properties of the star itself and the interstellar medium around it. In addition to spotting these distortions at the gates to interstellar space, the study also highlighted that the team was able to reconstruct the substantial differences in the heliosphere boundaries in recent years. This particular finding sheds new light on the journey of the Voyagers through the heliospheric termination shock, HTS, which is the point where the solar wind begins to slow, and subsequently through the heliopause. In the light of this, Zernstein said that the Voyager spacecraft provide the only direct, in situ measurement of the locations of these boundaries, but only at one point in space and time. So comparing their results, which were observed at a different time in the solar cycle than when Voyager 1 or 2 crossed the boundaries, made it complicated. The locations of the HTS surface compared well with Voyager 1 and 2, but what was most surprising surprising was the heliopause surface. Voyager 1 crossed the heliopause in 2012 at a distance of 121.6 AU from the Sun, while Voyager 2 crossed in 2018 at 119 AU. Zernstein and his colleagues discovered that the heliopause surface was actually shifting by tens of astronomical units over this time period. For instance, after Voyager 1 crossed this boundary, the heliopause expanded for years as if it were chasing it, though the border never overtook the probe again. In contrast, Voyager 2 may have been just inside the expanding heliopause for several years, like a surfer on the cusp of a wave, before it ultimately entered interstellar space. Zernstein explained that Voyager 2 crossed the HP in late 2018 at 119 AU from the Sun, and their analysis yielded a distance of 103 ± 8 AU in mid-2016, which is much closer to the Sun. However, he further explained that they know that Voyager 2 was still inside the heliopause in mid-2016, and quite close to the distance they derived within the analysis uncertainty. This implies that Voyager 2 was close to the heliopause in mid-2016, but just inside, and then the heliopause must have been moving outwards for a few years before the spacecraft eventually crossed it in late 2018. He added that both of these observations seem to imply significant motion of the heliopause surface over time, and how potentially close the Voyagers were to the heliopause at different times. In other words, the glow of the ENAs at this murky entrance to the wider galaxy have exposed the shifting borders of the heliosphere and illuminated strange structures that require more observations and simulations to explain. Given that we live inside this heliosphere, which protects our solar system from harmful cosmic radiation, it is important to map out its contours and understand the complex forces that shape it. To that end, Zernstein and his colleagues plan to continue exploring this region of space with IBEX and other missions, in the light of which Zernstein said that the next steps are twofold. Firstly, they would like to better understand the existence of this obliquity and the ripples, which probably will require comparisons with high-resolution, dynamic models of the heliosphere. It's likely that, with these new results, the outer heliosphere community will be motivated to improve their simulations in different aspects to try to understand the source of these observations. He concluded by highlighting that the other step is waiting for another big change in solar pressure, like what occurred in late 2014. It seems this kind of event may happen at least once per solar cycle, so in a few years, we may have another event to use for imaging the HTS and HP surfaces again. This may also coincide with the launch of NASA's Interstellar Mapping and Acceleration Probe, IMAP, in 2025, which will provide higher resolution observations of ENAs compared to IBEX, and even better pictures of the heliosphere for our space scientists. Next up, is there a fifth giant world in the solar system? The solar system is full of surprises. A new theory to explain how the solar system's gas giants got to their location involves an unknown fifth giant planet, lurking 80 billion kilometers from the Sun. Professor Seth Jacobson of Michigan State University said in a statement that our solar system has not always looked the way it does today. Throughout its history, the orbits of the planets have changed radically. He added that we can find out what happened, which I hope our scientists will soon find out. The research, also published in the journal Nature on April 27th, offers an explanation for what happened to gas giants in other solar systems and our own, namely Jupiter, Saturn, Uranus, and Neptune. That concludes today's video. Now, if you have found the content helpful, then don't forget to give this video a thumbs up and do subscribe to our channel for more contents like this. Thanks for watching and see you in the next video. Until then, goodbye.